Hello everyone, we will be starting soon, testing out the connection with Discord. Those of you who want to join through Discord, please feel free to do that. You'll be able to ask questions through Discord then. Hello chat. Hi Angie. Okay, that's great. So are you able to look at the YouTube and this at the same time, or maybe I should just also stream a second version here, and then you don't need to look at the YouTube. Say it again, Chad. Yes, there would be. Okay. Okay, so we can communicate through the Discord, and then I will be streaming whatever we're communicating anyway through YouTube, so whoever's watching there can watch there. But otherwise, the real-time communication will be through here. So I'm going to stream here as well. I'm just not sure. Okay, let me try to stream the whole screen instead of just a single window. It will be what, sorry? Yeah, I know. So I'm trying to do that. I wonder if everybody can hear you on YouTube. I have no idea at this point. That might be useful. Thanks. Okay, so let's try. So I'm streaming now the screen. I've got two screens on my desktop, and I'm streaming this screen that I'm using for YouTube. Can you but you can't hear any music, right? You can only hear my voice. Okay, that's probably coming through the microphone. Okay. Say it again. Oh, but so are you hearing music through the YouTube? I see. Okay. Okay, so you can see that professor there who is welcoming you to the live class, right? So that's where I'm going to be typing. Not typing, writing, yeah. Okay, well, maybe you can reconstruct the music from the graph. I don't know how to do that, so how do I share? Yeah. User settings, and then I go to voice and video, and I have input device, and if I switch to line, so let's try this. What's going on now? I guess now you can hear music, but you can't hear me. So was it the case that you could hear the music but not me? Oh, okay. Yeah, I don't think that it allows. Yeah, I don't think it allows input of more than one device. That's a good idea, yes. So, okay, so I think that if, yeah, I don't think at this point we will manage to do the math and music at the same time through Discord. So music is left only for the YouTube listeners. So if you have any question, you can I guess unmute yourself and then ask the question, right? What do you think about that? Now I'm wondering if the YouTube listeners are able to hear the conversation we are having. So could someone on YouTube please give us a guide to that? Maybe you can put it in the chat if you can hear myself talking with Chad. If you've been hearing the last discussion we've been having for the last few minutes. If there's anyone on YouTube, of course. Okay. Well, it's 5 o'clock, so we should start. So when I'll hear a question, then I'll repeat the question for the sake of the YouTube listeners, and then I will ask the question. Okay, yeah? Which link? Oh yes, the YouTube link. That's right. Yes, sorry, that's an important thing. So I'm gonna do that now. Chad, can I ask you to check if the link works? I have some doubts about the link. Okay, okay, great. Thank you for that. Okay, good, thanks. Oh, wow. Thank you. Okay, so hello everyone. We are going to have a couple of minutes delay. Thank you, Bella, for answering my question. We're going to have a couple of minutes delay until the YouTube streaming link has been shared on WhatsApp so that others can join as well. And so in these few minutes, let me just explain how we're going to work today. I'm now streaming through two places. One is the YouTube stream and the other one is the Discord stream. The link to the Discord stream has been shared on the WhatsApp group. And also the link to this YouTube stream is there. And so you can ask questions through either of the two options. If you're on Discord, you can connect with voice and ask a question like that. And I'll repeat your question for those of you who are not hearing the Discord voice, and then I'll answer the question. You can also still ask your questions through the YouTube chat and also through WhatsApp. And if I receive a question through WhatsApp, then the author of the question stays anonymous. Otherwise, I might say who is asking the question. Okay, so this afternoon will be also quite useful for me. Well, I hope it will be useful for you, but also for me because based on the kind of questions you ask me, I'm going to use that information from you to then decide what kind of videos to prepare for this last week, which is supposed to be the revision week. And let's get started. So I do not have any questions yet, I think. Okay, so no questions yet. And before the questions come in, let me just say something about an issue that several students have been asking me about. This is something that deals with turning a matrix into a set of eigenvectors when we solve the matrix. And I think the main confusion arises when one wants to make a shortcut. For example, if we have a matrix something like this, 1, 2, 3, 0, and then 0, 0, 2, and then 0, 0, 2. And then sometimes one isn't sure what to do here. What is the solution of this matrix and so on? But keep in mind that we're never solving the matrix actually. What we want to do is to solve a system of linear equations. A matrix is just a shorter way of presenting that system. So one shouldn't go directly from the matrix to the solution unless one is has mastered this really well, so that one can do that intermediate step in one's own mind. And so the right way to do this is to, when you have the matrix, what you want to do there is to move to the system of linear equations, which for this matrix will be, so each row of the matrix of course contributes with an equation. So we've got 1k1 plus 2k2 plus 3k3 equals 0. So that's for the coming from the first row, and then the second row is going to give 0k1 plus 0k2 plus 2k3 equals 0, and the third row is going to give 0k1 plus 0k2 plus 2k3 equals 0. But of course you might want to first simplify the matrix a bit with the row echelon reduction. That doesn't change the system of linear equations. It changes it, but it doesn't, whatever it changes it to, the thing is still equivalent to the original one. And so with the simplification here, the only thing that remains to do is to eliminate the third row, and then it will become the row of zeros, because you replace the third row by the difference of the second and the third one. And so that would result in the third row here being slightly different, right? So with a third row of that kind, you would have a 0 in the place of 2 here. And so then having an equation just with zeros will not affect the solution. And so it's the same as just erasing the whole thing. But even if you didn't go via the row echelon thing and you did the system directly, then because you see that the second and the third equation are the same, you could have erased this there as well. So the effect is the same. Okay, anyway, so now because the third equation doesn't matter anymore, we just deal with these two. And then the second equation there gives that k3 must be 0, since the only way this is 0 is if k3 is 0. And once k3 is 0, then there is k1 and k2 that's left, and then k1 can be expressed as minus 2 times k2. And so, oops, sorry, you couldn't see that. Okay, there we go. And then your solution, of course, is given by minus 2k2, k2, 0, and you can factor out the k2 there and just have minus 2, 1, 0 multiplied by k2. And then there is this whole business about spanning and basis that comes in that can tell us to just represent this thing as a single vector, because that single vector will span the whole eigenspace. Okay, so that's what I wanted to tell you before, while the questions were still arriving. So now I'm going to look at the questions that are there. I don't have any voice questions on Discord yet, but I do have some questions on YouTube live chat. Okay, Rowan Twiley is asking if I could just show how to prove that n by n matrix columns vectors are linearly independent from each other. Well, okay, so that's a good question. So if we have an n by n matrix, how can we prove that its columns will be linearly independent to each other? That's the question that came from the YouTube stream from Rowan. So let me show you this on an example. I think that will be most illustrative. So let's consider, for simplicity's sake, let's consider a 3 by 3 matrix, let's say, and suppose the columns of the 3 by 3 matrix are 1, 2, 3, 2, 3, 4, and 3, 5, 7. Okay. So if this is the matrix we are considering, and we want to find out whether its columns are linearly independent or not, I'm sorry, I'm just struggling a little bit with the screen showing, making sure the screen shows everywhere. So let me slightly fix this. Okay. I think I need to do this a little bit. And what I'm going to do on Discord is to just share the paint so that you have better visible space there. Okay, I think this should be better for Discord viewers. And okay, so I now see that the YouTube is fine. Great. So this is the matrix we have, and the question is whether the columns of this matrix are linearly independent or not. Now, for some reason, I can hear myself. I wonder through which source it is coming. Okay, I can't hear myself anymore. Maybe somebody else had a mic on, that's fine. Okay, great. So are the columns of this matrix linearly independent? That's the question. Well, what is the definition of linear independence? If we denote these columns by k1, maybe I shouldn't use k1 because we were using k1 for the entries of the k vector. Let me call these things c1. C1 is something else too. All right, let me call these things v1. V is a vector space. Oh dear, running out of letters there. Let me call this then a1, a2, a3. So these are the columns of the matrix A. Okay. Ryan Todd is asking if we suffer from Alzheimer's commercial or something like that. Is he our student or somebody coming from some other source? Anyway, so we have an interesting participant on YouTube stream there. So how do we show that the A1, A2, A3 columns are linearly independent? Well, what is linear independence? Linear independence says that if a linear combination of these is 0, then the coefficients that make the linear combination 0 are themselves 0. So that's the definition of linear independence. So this should hold for all values of C1, C2, C3, that every time this combination is 0, you want the C's to be 0. And when you now start checking whether this is the case or not, you remember the A1, A2, A3 are the columns. So this linear combination is actually nothing but the product of the matrix A with the column vector C1, C2, C3. Okay, I need to resize my screen a little bit. Sorry, a technical issue again. I want to make sure my screen fits everywhere. There we go. So the linear combination of the columns of A can be written out as the matrix A times the column vector of those coefficients making up the linear combination. And so checking for linear independence now becomes checking that if the matrix A multiplied by that column is equal to 0, then all the whole column must be 0 itself. So this is basically checking that the system of linear equations corresponding to the matrix A only has 0 solution. And isn't that beautiful? I mean, this is, wow, lots of balloons, right, coming out from this. So this is like fantastic. What a wonderful link between the notion of linear independence and and solving system of linear equations, right? So, okay, let's go back. So we had a matrix A. So this is the matrix A, whose columns are A1, A2, A3. So let's write them out this way. And we want to find out whether the columns of A are linearly independent or not. And so we write down the definition of linear independence, which is given by this. And then we examine what the left-hand side of this implication says. And we then come to the conclusion that this definition is actually saying that the system of linear equations corresponding to the matrix A only needs to have the zero solution. And that's where, by the way, we get this link with the determinant of A being non-zero. So now we've basically proved that columns of a matrix A will be linearly independent if and only if the determinant is non-zero. And so answering the original question we had, which was to find out how we can the question was to figure out how we can determine whether columns of a matrix are linearly independent or not. Now the answer to that is, well, there are several ways. The matrix A that you've got, write down the corresponding system of linear equations, and that the system needs to have only zero solution. That's one way. Another way, the determinant of the matrix shouldn't be zero. And so we've got two ways of finding out whether the columns of a matrix are linearly independent or not. Okay, great. I think I've answered the question. I'm going to move on to the next question now. I have nothing, it seems like I have nothing on the Discord, so I'm going to go to the YouTube questions. I'm quite behind actually. So I answered just now Robin Twiley's question. Thank you so much for this question. You see, the question led to a very interesting observation about the link between linear independence and the system of linear equations. Now the next question is by Chad. He's asking, okay, so I'm going to read it out. My question regarding eigenvectors and diagonalization. I notice some vectors were not normalized while others are. Do we only normalize in the case when we're dealing with diagonalization? No, you only normalize when you're dealing with orthogonal diagonalization. Only in the orthogonal diagonalization you need to normalize the eigenvectors, because in orthogonal diagonalization, so let me just put this in context for everyone. So diagonalization is a process when we want to produce the following equation out of a matrix A. So we want to find the P and the D that makes this equation hold. And with orthogonal diagonalization, we want the matrix P to be orthogonal matrix. And for it to be orthogonal matrix, its column vectors need to have norm 1, and also they need to be orthogonal to each other. And that's why we end up normalizing the vectors coming out, the eigenvectors coming out of A, because the columns of P are the eigenvectors of A. So it's only for orthogonal diagonalization that we need to normalize things. So that's answering Chad's question. Next question is by Honela. So could you go over why k3 equals 0 and not any real number? Okay, that's a very good question. So this goes back to what I was explaining here, right in here. And so the question is, why must k3 be 0 and not just any real number? Well, the whole point of a system of linear equations is that both equations in the system must hold, right? So this is like two people there demanding that their requests are met, but both of them are demanding a certain request, and we want to make both of them happy at the same time. And so the second person is demanding that the k1, k2, k3 are chosen in such a way that 0k1 plus 0k2 plus 0k3 equals 0. And so if you take k3 to be any number, 2 times k3 will not equal to 0, right? And so that's why k3 must be 0. That's the only way we can meet the demand of the second person. Of course, for the first person's demand, k3 doesn't have to be 0. But remember, we have to satisfy the demand of both people, not just one. It doesn't make, it makes no use to make one person in the country happy, you want to make everybody happy. And that's impossible in real life, but in mathematics it is. And so that's when you get that k3 must be 0 in order for both equations to be satisfied. So that's answering Honela's question. With the zero row, it's very different. So the second question he posted there was, what happens with the zero row? If you've got a zero row, then that's a person basically making a demand that, like this case here, if we did have 0 in the place of 2, then this person would have been making a demand that k1, k2, k3 are chosen in such a way that 0 times k1 plus 0 times k2 plus 0 times k3 is 0. But that means that there is no demand, because whatever k1, k2, k3 you pick, that thing will always be 0. So the third person is actually not demanding anything. He's a very flexible citizen. Okay, he made a certain demand, but the demand will be met no matter what we do. And so that's why his demand does not restrict the other two demands, because his demand can be satisfied by any possibility. So if it was only him and the other two hadn't been demanding anything, then the solution would have been any value of k1, k2, k3. But together with the others, because we have to make all three happy, we have to now consider the others as well, and that's where the k3 ends up being 0 because of the second person there. And there is no contribution from the third person, in the sense that the third person doesn't give any further restriction, because his demand was basically that he was happy with any option. Okay, so that explains, that answers the question by Honela. So then the next question is by Katie Me. I want to check with you, you do not have to normalize the matrix P if matrix A was a symmetric matrix, because it will automatically be orthogonal. Okay, so that's a very good question. So coming back to the orthogonalization, the diagonalization here, when A is symmetric matrix, we can find an orthogonal matrix P, but we have to search for it. Not just any set, any sequence of eigenvectors will constitute an orthogonal matrix. And so let me explain why. Let's say that A is a matrix whose eigenvectors are this vector here. So okay, let's say we're working in a three-dimensional space. So we've got 3 x's there, and okay, now the origin isn't where it should be. So these are the 3 x's, and let's say we've got a 3x3 matrix A, and its eigenvectors are the following. There are 2 eigenvectors for the same eigenvalue, and they both lie on the xy plane. Okay, so let's say the coordinates of these are 0, 1, 3, and 0, 3, 1, something like that, where this is the x-axis, this is the y-axis, and that's the z-axis. And so these two correspond for the eigenvalue lambda equals to, let's say 1, or maybe let's make it more interesting, lambda equals to 4. And suppose then there is a third eigenvector that now lies on the xy plane, so its coordinates are something like 1, 1, 0. And so that, let's say that one corresponds to, so the eigenspace is just a single line, and so that corresponds to the eigenvalue lambda equals to 2. Okay, so imagine a setup where you have a 3x3 matrix with eigenvalues being lambda equals 4 and lambda equals 2, and the eigenvectors being these 3 vectors. Well, these two are the representatives for the eigenspace for 4, and this one is a representative for a one-dimensional eigenspace corresponding to the eigenvalue lambda equals to 2. Now, if you take these 3 vectors and put them as columns of P, so let's do that. So let's call this one, let this be the first one, let this be the second one. Maybe I should give them some names like K1, K2, and K3. And so we put them as columns 0, 1, 3, 0, 3, 1, and 1, 1, 0. And this is the proposed matrix P. It's not going to work, right? Why is it not going to work? Well, it is a valid matrix for diagonalization, but this is not orthogonal diagonalization. So a symmetric matrix, okay, I forgot to say here, let's say that the 3 by 3 matrix is symmetric. A symmetric matrix, just like any other matrix, has various diagonalizations, but some of them are orthogonal ones. And in the problem of solving just the diagonalization problem, we don't care whether we pick orthogonal diagonalization or not. But if we are solving the orthogonal diagonalization problem, then we definitely want to pick the orthogonal one. And so the matrix P that we found here is not orthogonal. So let's make that remark. This is not orthogonal. Why is it not orthogonal? Well, because the columns are not unit vectors, and also because they're not orthogonal to each other. If you take the inner product of the two columns, you will not get, of the two different columns, you will not get 0. But it is possible to find an orthogonal matrix by fixing up the eigenvectors. Remember, the eigenvectors, the first two, for instance, come from the whole eigenspace, and the eigenspace is an infinite thing, right? It's the whole whole yz plane in the case of the eigenvalue 4. So what we want is to get a better pair of eigenvectors from that plane that are still linearly independent, but not just linearly independent, but also orthogonal to each other. So we can fix that up by either simply taking the unit vectors lying on the y and the z axis to be our new eigenvectors, or by keeping one of them and then fixing the other to be something that's orthogonal to the first one, and putting them in the place of the first two columns, and then also normalizing them to make sure that the lengths of these vectors are 1. As for the third column, we need to get something orthogonal on this line, but on this line we can get nothing, or I mean, we can get a unit vector, right, by shrinking this vector, but the problem is that now this line is not orthogonal to yz plane. And so there is no way to fix up this vector, because we have to, for eigenvalue lambda 2, we have to pick a vector from this line, but there is no way to make sure that this vector from this line will be orthogonal to the yz plane. So what's going on here? Well, what is going on here that it's impossible for a symmetric matrix to have exactly these 3 eigenvectors. And so the only way, if the k1 and the k2 are valid eigenvectors, the only way to have a third eigenvector for lambda equals to 2 would be something that will be orthogonal to everything on the yz plane. And so the only way is if it was a vector on the x-axis, but it isn't. And so because it isn't, actually the A matrix is not symmetric. It can't be symmetric. But if it was symmetric, then this line wouldn't have been here, this line would have been on the x-axis, and then we would be able to find the 3 orthogonal vectors and also normalize them to get the orthogonal matrix P. So that's the answer to Katimi's question. And now I'm moving on to the next question, which is Daniel Eggert is asking whether we only normalize when the inverse of P is equal to the transpose of P. Yes, a matrix P will be orthogonal exactly when its inverse is the transpose. That's the definition of being orthogonal. And that will happen exactly when the matrix A is symmetric, that you will be able to find such a matrix. Now, Honela is saying, I thought the 0 row meant K3 had to automatically be any real values. Well, no, it doesn't mean that. So if you have a row of zeros that doesn't yet suggest that K3 must be 0, we should also look at the other rows, because the other rows might give a different restriction on K3. So thanks, Honela, for that feedback. And then Hosea is saying, how do you visualize the P matrix tilting a linear map such that we represent its linear map as a diagonal matrix, like in normal coordinate systems on the new tilted coordinate system? Okay, I'm not sure I understand the question, but I'll give it a try. So what this question is referring to is the geometry behind the process of diagonalization. So if you've got, let's now make a simpler case of 2 by 2 matrices so that we can give the visuals more easily. So if we have a 2 by 2 matrix, what a 2 by 2 matrix does, it transforms a plane to itself. And with the process of diagonalization, what we're doing is we're changing the coordinate system. So we are finding new x's for which, you see, when we express a linear map as a matrix, it depends on the coordinate system we choose. So by changing the coordinate system, the matrix will change. And the matrix will change to a diagonal matrix when these x's from the new coordinate system are eigenvectors of the matrix A. And so now the question is, how do you visualize the P matrix? So the P matrix is the matrix of change of coordinate system. And I think the question is, well, I don't think we should visualize the P matrix itself. We could though. Okay, let's give it a try. So, okay, so first let's remind ourselves what the P matrix does. If you multiply a column with the P matrix, what you're going to get there, so this column gives new coordinates. The column itself, before we multiply by the matrix, x, y column are the new coordinates of the point. And P times that are the old coordinates. Okay, so how do we understand this? Remember, we have this equation P inverse A P equals D. So the way we understand this equation is that this linear map, when it acts on a column, the result should be the same as the D acting on the column. And so you see, D is the matrix for the new coordinate system. So these are the new coordinates of a vector, and you multiply it by the D matrix to get the new coordinates of the transformed vector. And so to do that, you first multiply by P to get the old coordinates, then you use the matrix A, which gives the output in terms of old coordinates, and then you multiply by P inverse to transform that old coordinate back to the new coordinates. Okay, so that's the procedure. Now the question is asking to visualize, I think the question is asking to visualize this process, the process of turning new coordinates to old coordinates. And I must be honest to you, I need to think about this question in order to answer it. So maybe let's try to think about it together. So, oops, what I'm going to do now, I'm going to copy this picture here. And so let's draw all of that. Okay, so what the matrix P does is that when you're given a vector with new coordinates being x, y, that means that when you project this point, so this is the initial point we're given, whose coordinates are x and y on the new axis. Now, when we multiply by the matrix P, we are going to get coordinates on the old axis. Right? So these coordinates, so if I multiply this by P, I will get some, let's call it x prime, y prime, although these are not derivatives of x and y. And so this is what we get here. And I still don't know how to answer the question. I don't see any, I don't think I have any visual way of seeing what's going on here. Because, I mean, you might have thought that maybe it's simply rotating and matching the orange coordinate on the white coordinate, but that's definitely not what's happening, right? If I rotate this, this point is going to move somewhere here, and it's definitely not going to be a similar location as the point there with those coordinates. So I'm sorry who asked that question. Let me try to see. Yeah, to Hosea. I do not know the answer to your question, and I do not know if it's possible to give a nice answer to that question. Unless you wanted to ask something slightly different than what I tried to answer, so if you might want to revise your question. Otherwise, I don't know the answer to your question. But it's an interesting question, and so if someone finds an answer to that question, please do share with everyone else. Okay, so Holonella, but okay, let me just go back to that. So I do not know how to visualize it, but it doesn't mean that we don't know what it means. So what the matrix P means is it's a matrix that allows you to change from new coordinates to the old coordinates. It's just that the visual part is something that we're struggling to figure out. Okay, except this picture, which shows visually how you, having old coordinates, you can get the new coordinates. But I don't think that's what you were asking. Okay, great. Now, after that, there was a question by Holonella again. In example video 2 of this week, we got 2 eigenvectors from the first eigenvalue. Luckily, they were linearly independent. If they weren't, how would you fix them? By choosing other values? Okay, so let's answer that question. So in the situation where you end up getting something that's linearly independent, an example of such a situation is when you have your solution to the eigenspace being, let's say, something like this: t plus s, t minus s. Maybe we get something like that. Actually, we never get something like that, right? We always get t somewhere, and then okay, so t 2t, but we need 2 of them. Okay, so something like this. Okay, before I move on with this, I saw now a comment by Hosea that he meant, how does P transform the coordinate system? I guess you meant to ask, why does it transform the coordinate system? Yeah, I think that question is answered in one of my example videos, and the brief answer is in the picture here, but it doesn't answer why this is so. Okay, maybe that's not so difficult to see why. Yeah, Hosea, I'm going to come back to your question. It's a good question, and I'm going to answer that question. So the question there is, why is it that multiplying by matrix P is the same as changing the coordinates system? Give me a feedback on that if I'm understanding your question right this time, and if I am, then I'm going to answer that question later on. So when we have eigenspace that's given like this, so let's say this is eigenspace, and now, so to be more precise, the eigenspace is the set of all vectors of this form where t and s are real numbers. And now the question is, how do we pick out from this eigenspace its basis? A basis is something that should be linearly independent, and at the same time it should span the entire space. Okay, when we see a vector here given by 2 parameters, the initial reaction we have to this is that since there are 2 parameters, then probably this is a 2-dimensional space, so the basis will have 2 vectors in it. And so since the basis will have 2 vectors, I can just pick t to be 1, s to be 0, and then t to be 0 and s to be 1, and this way isolate the 2 vectors, and if I'm lucky, then these 2 are going to be linearly independent, and I've then found the basis, because if you've got 2 linearly independent vectors in a 2-dimensional space, then this will definitely be the basis of that space. But now, what is a more canonical way of approaching this question? And the answer is the following. So what you want to do is to represent this vector as a linear combination of two specific vectors. And so you can do that by the method that almost always works. By almost, I mean I don't even have an idea how to write down an example that doesn't work straight away off from my head, is that you separate the parameters like this, and then you take the t out, you get 2, 1, 0, and then here you get 0, 0, 1. And after this representation, all you need to check is that these two are linearly independent. And if they are, then you're done, because you know that these two span the space, since anything in the space is a linear combination of those two. So they span, so this requirement is satisfied, and you also know that they're linearly independent. Why? Because you can check that one of them isn't a multiple of the other. Okay, but now, just by separating the parameters, it works. But now let's consider a situation where this method might not have worked. For example, let's consider a situation of this kind. No, I said I couldn't come up with an example, but maybe I can. T, and then here we have, well, t plus s. This is going to be an easy one. 2t plus 2s and 3t. Okay. Now, if here I'll try to separate, the vectors I'm going to get will be t, 1, 2, 3, plus s, 1, 2, 0, right? And again, it works. But if I didn't have 3t here, if I had a 0 here, then we would have a 0 here as well, and then it doesn't work in the sense that we get these two that are these identical vectors. So they're not linearly independent. And of course, what's going on here is that we can reparameterize this whole thing by setting this to be some parameter u and the other one to be just 2 times u. And so we see that in fact we could have reduced the number of parameters, and then we wouldn't have run through the confusion that this could be a two-dimensional eigenspace. It is not really such a big trouble of separating the linearly independent eigenvectors, because the way you would have arrived to this solution is that you would have expressed, you would have had some free parameters, and then others would have been combinations of those. And I think in all such cases, if you solve the system of linear equations correctly, you will automatically get linearly independent ones by separation. The more subtle point, and I think that's the one that that was meant in the question, is how do we make sure what we get here are orthogonal to each other? So here, accidentally, they're not just linearly independent, they're also orthogonal to each other. But there might not always be orthogonal to each other. And here is an example, and that's, I think, the same example that Chad was suggesting on the chat. So let's say we have s, t, and then we have s plus t. If we try to separate these, we'll get 1, 0, 1, and for t, we'll get 0, 1, 1. And now these two vectors, they're still linearly independent, but so these two are still linearly independent, but not orthogonal to each other. And so now the question is, what do we do here? This question would only arise if we are trying to solve an orthogonal diagonalization problem. And the question is, how do we get them to be orthogonal? Because the thing we get out from just direct manipulation is not orthogonal. And so what we need to do there is the following. I mean, what we could do there is the following. So we could keep one vector. Let's say we keep 1, 0, 1 vector. Okay? And for the other one, we need to have some kind of linear combination, I mean, some kind of vector of this form, which would be orthogonal to 1, 0, 1. So remember what's going on here? The eigenspace consists of all vectors of this form, right? And so that's the same as all vectors of that form. And one of them is the vector 1, 0, 1. Now, we need another one. And initially we picked this to be the other one, but that other one was not orthogonal to the first one. We need one that is orthogonal. So what we do now is we write down it in a general form. We don't know yet what should S and T be. We don't know how to choose them yet in such a way that they will be orthogonal. But then it's very easy to figure out how to choose them, because we write down what it means for them to be orthogonal, for this vector to be orthogonal to the first one. It means that the this inner product is 0, right? So this is orthogonality of the two vectors. So these two are orthogonal if and only if that will be 0. And now you see what's going on. This is another absolute marvel of mathematics. So you basically write down what you want, and what you want is something that you can solve, and then you get the answer. And so you were looking for something, you didn't know how to find it, you just wrote down what you wanted to find, and then you find it just by means of writing down of what you wanted to find. Okay, so we wanted to find another vector that's orthogonal to the first one. We didn't know how to find it, we had no idea. Okay, but we wrote down instead what it means for them to be orthogonal to each other. And it means this to be 0. And now, if I expand this, this says that s plus t needs to be 0. And that is equivalent to being orthogonal. So any values of s and t that we choose that makes 2s plus t equals 0 is going to be fine. And for example, we could pick t equals 0 and s equals 0, right? Oops, that's not good. Because if we pick both of them to be 0, we get the 0 vector. And then we don't want the 0 vector to be eigenvector. Okay, so let's try again. Let's pick t to be 1 instead. And then let's pick s to be minus a half. Maybe let's make a nicer number. Let's pick t to be minus 2 and s to be 1. I'm just picking random values. I could have done anything I liked. I just need one single orthogonal vector. I don't need all of them, right? I just need one. So I'm not going to say like t can be anything and then s must be that and that, because I just need one single thing there. So this would work. And now to check that it does work, I write down my two vectors. So the first one was this, and then the second one will be given by s being 1 and t being minus 2. So I'm substituting those values into the vector. And so the last one will be the sum of those, so it will be minus 1. And now when I take their inner product, 1 times 1 plus 0 times minus 2 plus 1 times minus 1, that does end up being 0. So these two now are orthogonal. So this is a very easy method that you can use instead of that complicated Gram-Schmidt business. Okay. You just write down what it means for the second vector to be orthogonal to the first one. You represent the second vector in the form that you know it should have if it's in the eigenspace, and then you solve it, and then you got a whole infinitely many solutions there, and then you pick one of them. But of course, afterwards, when you normalize those vectors, it will not be infinitely many anymore. But we're not discussing normalization now. We're just discussing how we pick out the orthogonal ones. I think that's what the question actually meant, because in the example video where I said that accidentally we got something to be orthogonal, linearly independent, it wasn't really linearly independent that was the accident. It was the orthogonality that was the accident. And so now I explain how to what to do in a situation where the accident does not happen and we don't get something that's by default orthogonal. Okay, great. So that answers Honella's next question. And then there is another question. Okay, so now Jose says that my interpretation of his question was right. So I'm going to ask that. Sorry, I'm going to talk about that now. I'm wondering though now what is the point of the Discord, because I'm not communicating with anyone on Discord. Maybe after answering Jose's question we can have a little bit of a chat over Discord to see if everybody's still... Oh, but I also see that nobody is on Discord anymore. I think. Anyway. Okay, so let's go back to Jose's question. And it's a very interesting question. So in the whole business of orthogonal diagonalization, and in particular when we wanted to sketch the curve given by a certain equation, we mentioned there that what orthogonal diagonalization is really about is finding a new coordinate system given by the matrix P. And what we want to understand is how does that work. So if I have a certain matrix P, and I'm going to work on an example here. So let's say the matrix P is given by the following values. 1 over square root of 2, 1 over square root of 2, and I'm picking an orthogonal matrix deliberately to make calculations easier. And well, let's hope I'll make those calculations easier that way. And then minus 1 over square root of 2 and 1 over square root of 2. So that's the matrix we want to work with. So according to that matrix, the new coordinate system should be given by the columns of that matrix, which is 1 over square root of 2, 1 over square root of 2. And remember, these are the old coordinates of the new coordinate system, right? So 1 over square root of 2 is this number here, the old coordinate. Maybe I should use white color for that, for the old coordinates. So the orange vectors are the new coordinate system vectors, but their old coordinates is what goes inside the matrix P. And so they are, so let me actually write them as columns. 1 over square root of 2, 1 over square root of 2. And you can see why that vector will lie there. So there is 1 over square root of 2 there. And of course the length of that such a vector will be 1, right? And here we have also minus 1 over square root of 2. So that vector is 1 over square root of 2 minus 1 over square root of 2. Okay, now why is it that if I take a vector in a new coordinate system, and let this be the vector, now let me write on in orange, x, y, and so the x and the y are coordinates of this vector in the new coordinate system. What does that mean? Let's denote this vector by v1 and that vector by v2. For this to have coordinates v1 and v2 in the new coordinate system, it means that when I take that vector, so let's say the vector is here. How do we get coordinates of a vector? We get it by projecting here and there, right? And so we end up expressing this vector as a linear combination of v1 and v2, and whatever coefficients are in that expression will be the new coordinates. So vector xy in the new coordinate system, if the x and y are the coordinates in the new system, then that's going to be linear combination of x of the following form: x v1 plus y v2. That's what it means for x and y to be coordinates for some coordinate system v1 v2. It means for xy vector, so let's call this vector k, okay? So what I'm saying here is that for the vector k to have x and y coordinates in the new system, in the orange system, that means for k to be equal to x times v1 plus y times v2, where v1 and v2 are the vectors of the, they are the vectors that give the coordinate system itself, okay? They're the coordinate system vectors. Okay, so I hope it's clear for everyone what I'm talking about here. So coordinates of a vector relative to some system is the values that you get by expressing that vector as a linear combination of the coordinate vectors. Okay, but now if I want to find the old coordinates of the vector k, well, now I know that k is equal to this linear combination of v1 and v2, right? So if I know the old coordinates of v1 and old coordinates of v2, I can just sub it in here to get old coordinates of k. So this is when this orange equation starts to transform into a white equation. Why? The rule that x equals to k equals to x v1 plus y v2, that rule doesn't change. It's still the same linear combination, this parallelogram rule that gives me that decomposition of k in terms of scalar multiples of v1 and v2, that geometric picture here does not care which coordinate system we're working in, right? So now having that k is still a linear combination of v1 and v2, and knowing what v1 and v2 are, what are they? The coordinates of v1 and v2 are 1 over square root of 2, 1 over square root of 2, and for v2 it's 1 over square root of 2 minus 1 over square root of sorry, the other way around. This should be minus here, and no, it's right. Minus is there. Okay, so what I've done here, I've just subbed in the old coordinates of v1 and v2. I know that the k vector is equal to that linear combination, so then I will have k vector being equal to that. But what is this? This is nothing but the matrix 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2 minus 1 over square root of 2. That matrix being multiplied by the column vector xy. And so that's exactly the matrix P multiplied by xy. And that's why you get your k now in terms of the old coordinates, right? Because now we know that k is equal to this thing, and in terms of old coordinates, that thing is this thing, and so it's this thing. So this thing here, p times xy vector, gives then the old coordinates of the vector k. I hope that was a clear explanation, Jose. If you have a further question, please feel free to ask that. It's a bit subtle theoretical point. You might want to maybe run through this argument yourself and kind of convince yourself. So the main point there is to know what it means for something to have a coordinates. And so for new coordinates to be x and y, it means k to be that linear combination. And once we know that this relationship holds between k and v1 and v2, the relationship I'm referring to is this. Once we know this relationship holds, we can now interpret this relationship also in the old coordinate system, and interpreting that relationship in the old coordinate system gives us that k is equal to p times the column vector xy. And that relationship now is in the old coordinate system. This relationship here is independent of the coordinate system. It's a relationship, a certain vector is such a linear combination of the v1 and v2. And what plays a major role here is, of course, that the two coordinate systems have the same origin. If I displace the origin, I would get still further formulas for computation. But the origin of the coordinate system in both cases is the same. And because the origin is the same, this relationship does not change when we switch from one coordinate system to the other. So it gives us a way of transitioning from one coordinate system to the other. It's some relationship that's invariant under the coordinate system. But then interpreting this relationship, okay, let's check how we interpret this relationship in the new coordinate system to convince you of my argument a bit better, if you're not convinced yet. So in the new coordinate system, I'm going to use orange color for that. K has certain coordinates, we don't know what they are yet. And v1, what are the coordinates of v1 in the new coordinate system? Remember, v1 is itself the coordinate vector, so its coordinates must be 1, 0. And v2 is the vector 0, 1, right? In the v1, v2 coordinate system, the coordinates of v1 are that, and the coordinates of v2 are that, right? And so now, when I work out the sum, I'm going to get, of course, the vector xy. So you can see here that x and y are coordinates in the new coordinate system, whereas in the old coordinate system they are given by xy times the matrix P. Okay. Great. I think Hosea is happy with my answer, which is fantastic because I was getting a bit of a feeling that maybe not everything was clear. So we have a little 2 or 3 minute break now. No, we don't anymore because there is still Chad on Discord. So let's see what Chad has to say. Hello, Chad. Would you like to say hello? Is there anything that you want to talk about, or anyone else who wants to join via Discord while I'm waiting for further questions? I think I've answered all the questions so far. No response from Chad. Okay, no problem. Then I'm just going to explain to you something from my mind while any new question is gonna come in. The idea is that the stream is from 5 to 7, so we still have 1 more hour, but maybe everybody wants to take a break. Why don't we have a break of 2 or 3 minutes indeed, and also I'm gonna rest my voice a little bit. I'm putting the music volume up for the break. And I'm going to actually mute the microphone for a little. All right, hello everyone again. So we are continuing the live stream. At this point, Chad did ask me some questions on Discord, and I answered them without having to draw anything. So if anyone else has any questions, please let me know about that. Otherwise, I'm going to try to see what I can tell you that might be interesting and useful for you in terms of the work in engineering mathematics. Okay, so yeah, just the background maybe to someone who randomly is tuned in here and is not sure what's going on. At the moment we are discussing some mathematics that's relevant to engineering from a specific course called Engineering Mathematics at Stellenbosch University. Right, so from the topic of eigenvectors and eigenvalues, I feel like everything has been addressed in this session and also the past session. So I'm not sure I want to add anything there unless there is a special request. There is, however, a lot of things to say from the topic of vector spaces, and specifically in terms of finding the... Oh, great! I was struggling now here to figure out what to say next, but Daniel says I should look at WhatsApp. Oh, right. The request is to work through online tutorial tests, and specifically the first question from there. I hope this test has already been written and we're not doing something illegal here. So let's have a look at that. So this is a very interesting question, it seems. We have, in this question, we have a set V. Okay, so that does deal with vector spaces. V is the set R squared. So the vectors in this space are going to be pairs of real numbers. But it's not the usual R squared vector space that we're working with here, but rather it's slight modification where addition of vectors is defined in a very strange way, and namely in the following way: x1, y1, so which represents a single vector in R squared, plus x2, y2, which represents another vector in R squared, is equal. So this is the definition of addition in a new space we're trying to build. I guess the question will be asking whether this is a space at all or not. It's equal to x1 times x2, y1 times y2. And multiplication by scalars is also defined in the following way: k times xy is equal to kx. So that's the usual way we would want to multiply vectors with scalars, right? And so that's again by definition. And now the question is asking, the statements below state that V satisfies a particular vector space axiom under the addition and scalar multiplication given above. Select only those statements that are false. Okay, so let's have a look at the multiple choice options. I don't have them with me, but it will be provided on WhatsApp, so they'll be coming through in a moment. And so basically what this question will be about is to verify which axioms hold and which axioms do not hold for this structure. So the structure we're dealing with here is given by a set V, which is the set of real ordered pairs of real numbers, and addition and scalar multiplication defined in this way. Okay, so we are going to be actually looking at all the axioms and trying to verify them one by one. So let's do that. The first one we want to verify is if two things are in V. So let's number them. The first axiom to verify Maybe I'm going to use an orange color for numbering the axioms. Okay. So the first axiom says that if two things are in V, so if let's say x and y are in V, then their sum is in V. And we can see from this definition that if I take two pairs of real, two ordered pairs of real numbers, the way the sum was defined, it will still be an ordered pair of real numbers, right? So this is fine, this is correct. Second, is that if we have x and y from V, so x and y will always represent something from V, I will not write that out, that x plus y is equal to y plus x. Now if you think about this, if I edit them the other way around, the order changed, the effect it would have on the answer is that the order in each product here would change, right? That they would swap around. And with the swapped around order, the products are still the same. So because the order doesn't matter in multiplication, then it will also follow that the order will not matter in addition. So that's also fine. The third one says, so you see what it means to confirm an axiom. You just apply the axiom for the structure that's defined, and you write down what it means for that structure, that axiom to hold, and then you check if it holds or not. We haven't been writing this down yet. I mean, we haven't been explicitly writing down what they mean because we were able to get to the answer quickly. But in some other cases where it will be longer work, we will have a chance to write them out more explicitly. So the third one is, okay, maybe this is the one where we should be more careful. We want to check that x plus y plus z is equal to x plus y plus z. Okay, well, in this space we're working with, x, y, z, each of them are ordered pairs of numbers, right? So let's write them as ordered pairs. Let's write x as x1, x2. Let's write y as y1, y2. And let's write z as z1, z2. And now, let's start making computation of what is x plus y plus z. So the first thing we want to do here is to compute what is y plus z. And because then that will be added to x, right? And well, y plus z, if I put in there the y1, y2, z1, z2, and if I apply the definition of addition, the one I've got here, in order to add y and z, what I need to do is I need to multiply the corresponding coordinates, right? So I will get here a pair consisting of y1 times z1 and y2 times z2. So that's the pair that's being added to the vector x. And now I'm going to iterate this process. So now this is the pair that's being added to x, and x itself is a pair, right? It's the pair consisting of x1 and x2. And how do I add pairs in this structure? By multiplying the corresponding coordinates. So their sum will be x1 times y1 times z1, and here we'll have x2 times y2 times z2. And if you work out the other expression, the right hand side of the equality that we want to establish, on the other side we will have something very similar. I'm not going to do the steps there anymore. What we will have there will be the pair consisting of x1 times y1 times z1, and then x2 times y2 times z2. And now comparing whether these two are equal or not reduces to comparing whether these two are equal or not, and of course they are. Why? Because for multiplication we've got this equality. You see, it's a similar law that we're using for multiplication that we want to establish for addition, and isn't that nice? And it kind of makes sense because we wanted to establish that a certain law holds for addition, namely this law, but addition was defined in terms of multiplication through the coordinates, right? And so it kind of makes sense that validity of this law has reduced to verifying the same law, but now not for addition, but for multiplication. You see the bracket, the rearrangement of brackets is exactly the same as we wanted to work out here. And so the answer is yes then, and so this axiom does hold. How am I doing, Daniel? Tell me if I should make the explanations more detailed or less detailed. The fourth one says that there is unique vector 0 in V such that x plus 0 equals x equals 0 plus x. Now the thing is that if we had the usual vector space, the usual r squared vector space, where the structure of addition was the usual one in terms of adding the coordinates, then in that vector space the 0 vector is given by the pair 0, 0, right? But here we have a different vector space. We have a vector space where addition is given by multiplication. So that's 0 vector might no longer work here. We might have to find a different 0 vector. And so to understand which 0 vector would we have to find, what we want to do is to rewrite this orange equation in terms of how the addition is defined. And to do that, first I'm going to express x as an ordered pair, because that's what an object in V looks like. And then 0 also is some ordered pair, 0, 1, 0, 2. And these 0, 1 and 0, 2 at this point are unknown. We don't know what they are. We don't know where they come from. Right? We don't even know if they exist. And so what we want from them is that x plus 0 must be equal to x. But what is x plus 0? X plus 0 is x1 times 0, 1, x2 times 0, 2, right? That needs to equal x. In other words, it needs to equal x1, x2. So that's the first equation there. We also want 0 plus x to equal x, right? So many demands, right? This mathematics sometimes appears to be very demanding subject, doesn't it? So we also want this to be equal to x1, x2. Now the question here is, can we find something like this that would make both of these hold? But that should hold for every x, remember. And moreover, 0 cannot depend on x. 0 must be independent of x. No matter what x we pick, it's the same 0, 1 and 0, 2 that should work to make these two hold. Is there such 0, 1 and 0, 2? Well, after a lot of struggle and a few sleepless nights, we might figure out, well, I guess test was only open for 1 day, so you needed to have sleepless nights before the test. So then we can figure out that that was something rude. I said it was just for the sake of a joke. I apologize for that. So please don't have sleepless nights before the test. So we need to have 0, 1 equals 1 and 0, 2 equals 2. Oh, sorry, not 2, equals 1 again. Indeed, if I pick 0, 1 to be 1 and 0 to be 1, and I put it in here, both of these equations will hold. So the 0 vector in this new strange space we are working with is not the vector 0, 0, it's the vector 1, 1. So this does hold with the 0 vector being the vector 1, 1. Now, isn't that quite remarkable? Out of the way usual 0 vector, now we are friends with the 1, 1 vector. Okay, so that's the fourth axiom. Now let's have a look at the fifth axiom. The fifth axiom, by the way, some of these axioms are actually redundant, but that's not my fault. That's neither the fault of the one who prepared the test, it's the fault of the textbook, which has many other faults as well, like we all do. Okay, so the fifth one says that for hx, the wording here is very important because it gives logical dependence of variables. For each x in V, there is another vector minus x is again in V, such, again some requirements are placed, but this time this other thing, the minus x, now depends on x. You see, previously 0 was independent of x, and how could we tell that it was independent? Well, first of all, in the notation there was no x. Secondly, we spoke of 0 before we spoke of x. Here we're speaking of minus x after we are speaking of x, and that shows the dependence. Okay, so for each x in V there must be some other vector which depends on the x vector, so that we write it as 0 as minus x, and that doesn't have to be the usual minus, by the way, such that x plus minus x is going to be equal to 0. But now we know what is 0, right? 0 is not the 0 vector. 0 is the vector 1 1, right? 0 is the vector 1 1. Let's remember that, but just for a few minutes, because that only works in this specific very strange vector space. X plus minus x must equal to the vector 1 1, and also minus x plus x needs to equal vector 1 1. And this is another tough one. How to figure this out? Well, the only way is to first write out what x is. It's given by x1 and x2, and then well, then minus x will be given by some variables, let's call it a, b, and keeping in mind that they can depend on the x1 and x2. So there are some functions of x1 and x2. Maybe I want to write them this way. A is a function of x1 and x2, and so is b. And what we want here is that x plus minus x, but now we know what is x plus minus x once we know the pairs, right? So that's going to be, well, we want this to be 1 1, and so if we add these two things, by the rule how we add these things, it's going to be x1 times a of x1 x2 and x2 times b of x1 x2, and that needs to equal to 1 1. So this is one equation we have. There is also another one, but guess what? The other one can be disregarded. This other equation will follow from the axiom 2 that we established. In axiom 2, we saw that it doesn't make a difference in which order are we adding the vectors. X plus y is the same as y plus x, right? So since x plus y is the same as y plus x, going back here, x plus minus x will be the same as minus x plus x. And if we show that x plus minus x is 1 1, we no longer need to show the other one, because then the other one will come free from the fact that these two are equal. So this follows from the second axiom that we already validated to be true in this structure. So we only need to check for one equality, but more precisely we need to find the a function and the b function, both of which are function of x1 and x2, so that this will hold. Now, in order for this equality of ordered pairs to hold, what we need is that each component should be equal to the corresponding component, right? So this needs to be equal to that, and that thing needs to be equal to that. Okay, can you think of some value for ax1, x2, so that multiplied by x1 it will give you 1? I'm gonna give you a little time to think about this, and please give me your answers on the chat. Is it possible, the question is it possible to find the a and the b, and if it is, what are they equal to? In order that, so that x1 times that thing is going to be 1, and x2 times that thing is going to be 1 as well, no matter what x1 and x2 are. But a and the b can depend on x1 and x2. So let me repeat the question. Is it possible to find a and a b such that x1 times a is going to be 1 and x1 times b is going to be 1, no matter what x1 and x2 we've started with the a and the b being allowed to be dependent on the choice of x1 and x2? Okay, I'm not getting any answers yet. Maybe somebody wants to answer it on Discord. No answers yet. It looks like this is a difficult question. I don't see why it is a difficult question. Okay, so someone just said that if they had to guess, they would think so. Okay, so then what should be A? Well, if we want x1 times A to be 1, then A has to be 1 over x1, right? And if we want x2 times B to be 1, then B has to be 1 over x2. But there is a problem with this. What is the problem? If x1 is 0, 1 over x1 is not defined. And indeed, if x1 is 0, we will not be able to multiply it by anything to get 1 as a result. So it's impossible to find the A and the B in the case when either x1 or the x2 is 0. So this axiom fails. Why? Because minus 1 does not exist when x has the form or that form. So for those two types of vectors, minus x does not exist, and hence the axiom fails because the axiom requires it to exist for every x in the vector space. Okay, so that's the first one that has failed so far. No other has failed so far, but now we know that one does. That one does fail. And then the sixth axiom asks that, so that's the sixth one is easy one. It asks that the scalar multiple of a vector is still a vector. So if we've got an x in V, then also k times x for any scalar k will be in V. And that's definitely the case because if I go back to how the scalar multiplication was defined, you see the output of that is still an ordered pair of real numbers. So whatever ordered pair you multiply by k, still you get an ordered pair of real numbers, so you're still inside the set r squared. So axiom 6 holds. And then the axiom 7 asks if it is true or not that k times x plus y is equal to k times x plus k times y. And so let's see if that's true or not by writing down x as a pair x1 x2, and the same for y. Y is a pair y1 y2. And now what is going to be k times the sum of the two? So k times x plus y is going to be, well, we know how to add those two, right? According to the rule we introduced, we should add them by multiplying their coordinates. So and then when we multiply by the scalar k, that scalar k multiplies inside each coordinate. So the answer to this is this. Okay, so the intermediate step here is that this is the same as k times that ordered pair plus that ordered pair, which is x1 y1 x2 y2, and then that's the same as this because that's how scalar multiplication was defined in this new vector space. Well, it's not a vector space anymore because the condition 5 fails, but the structure that we wanted to test for being a vector space or not. Okay, so that's the left hand side. What about the right hand side? Well, the right hand side will have kx1 kx2 plus ky1 ky2, right? And when we add these two, according to the way we define addition, we have to multiply the coordinates, and it will give us k squared x1 k squared k squared x1 times y1 and k squared x2 times y2. And we see that in general this thing this thing will not necessarily be equal to that thing because of that k squared thing, right? So here also we get a failure. It does not work. As soon as we have a k that's not equal to 1 or minus, well, minus 1 also wouldn't work. So one can choose numbers for k, x1 and y1. Of course, one can easily find those numbers to make this fail to equal to that, and therefore to break this equality. So number 7 doesn't work either. And then there are 3 more axioms to check. Number 8 also will not work, I think, because it's about k plus k2. Wait a second, maybe that could work. Multiplied by x equals k1x plus k2x. So let's try to figure this out. The left hand side will have the form k1 plus k2 multiplied by the pair x1 x2. Now I'm using that pair representation of x as before. The right hand side, on the other hand, will have k1 x1 x2 plus k2 x1 x2. And so the left hand side, by the way we multiply scalars in, is going to be k1 plus k2 times x1 and k1 plus k2 times x2. Whereas the right hand side will be what? K will go in here, and then when we add it, it will multiply across, right? So it will be k1 k2 x1 squared k1 k2 x2 squared, and certainly this is not true that this is always equal to the other one. So that axiom also fails. I don't know why I thought it would work. I feel stupid now. It definitely doesn't work for huge reasons, right? The left hand side here is completely different to the right hand side there. Then there is another one that says that k1 times k2 and that times x must be equal to k1 times k2 times x, and that will work. Why? Because here we are only using multiplication, and multiplication of a vector by a scalar, and multiplication was defined in the same way of a vector by a scalar is defined in the same way as it is in the R squared space, and there we know it works. So here it works as well, because here nothing is different from the R squared space, since there is no addition that we're making use of this. Remember, in our structure it's the addition that's different from the usual thing. And then the last axiom says that we need to have 1 times, and again 1 times x equals x, and that's true because again we're only making use of the part of the structure that's common to usual R squared space where we know this holds. So the axioms that do not hold are the are axiom 8, axiom 7, and axiom 5. So that's the solution to that question there. Apparently it's from a test. Okay, I think it matches with the one given in the memorandum. Anyhow, so that's answering a request. Any other questions? I didn't have any other questions arriving. It was a long one, this one, because we had to check lots of axioms, but I hope it kind of made clear how something like that is done. I do discuss in the written lecture the topic of verifying whether axioms hold or not. So if you need some more systematic material on that, look at my written lecture from the corresponding week's work. Okay, so we are again into a situation where there are no more questions coming in from the audience, and I am thinking now, okay, what could we do? Maybe I want to make a little announcement in this little break. So I would really like you to give me some indications as to the topics on which you would like me to prepare videos for the revision week. I have a certain plan I'm going to follow. I'm going to be preparing some videos for the revision week. So the idea of this whole week next week is to revise the material so that you prepare for the A2 paper and also the A3 paper afterwards. And so I will be making videos in light of that. But if there are any special requests from students to include explanation of certain topics, that will be fantastic. And so please send in those requests. By the way, you are also welcome, unless I will quickly get overloaded, but I don't think I will, you're also welcome to send me your own videos where you explain something, and the purpose of that would be either for me to see how you're approaching a question and to give you a feedback on that, or to share your video with others. So if you want your math explanation video to be shared with others in the revision week, send it through. I'm going to look at the video, and then if I find it appropriate, then I'm going to share it with others as well if you want to. Chad is asking what you should do in the revision week. Well, I thought I just said that. No, sorry. I don't know who is asking. Oh, I see. Now I understand. Okay, one person was asking another person. Okay, so Chad, we just did a proof for a vector space, and so maybe you want me to look at an example now where we try to establish whether something is a subspace or not, or is it something that you want us to do in the revision week? I think I'm not following exactly which of the two you mean. You can just also tell me by voice because it's quiet over here. A 2-minute break before we decide how we continue on. All right, I'm back. I don't have any questions so far. Maybe I should ask Daniel if he's happy with what we did here with that question from the test. Okay, so let us we still have like 20 minutes left, so let's do something interesting in these 20 minutes. Maybe I want to do a little bit of maybe like a 3 or 4 minute summary of how the topics that we've done this semester kind of link up. So the common thread of the first term and the second term, I think, is linear independence. So linear independence is used in the theory of okay, thank you, Daniel. In the theory of linear differential equations, and also in the theory of matrices. And the concept of a vector space, you can kind of think of it as a language which allows us to express the definition of linear independence. So it's the context in which the definition makes sense. Because remember, for linear independence of functions, which is what we have for differential equations, we needed the objects we're considering to be functions. With matrices, we need them to be column vectors, and now a column vector seems to be something very different from a function. So how do we put them all together? And the answer is, well, one way of putting them together is to talk about abstract vector spaces. But now vector spaces also enter story in a different way, in a deeper way, because it's actually not just linear independence that was common to both. Another important commonality is the notion of dimension. So how do we see dimension in the theory of matrices? I'm not talking about the dimension of the matrix, I'm talking about dimension of a subspace. We see it through, maybe I should make this link here. So we had here something called fundamental set. No, sorry, we had a solution of the homogeneous linear differential equation, and here we have eigenspace, which is solution, all eigenvectors that are solutions of the eigenvalue problem. So it's a solution of homogeneous linear differential equation. And so when we're writing down the solution of a homogeneous linear differential equation, we had an expression of the form y equals c1y1 plus c2y2, right? And something like that. Maybe there are many of them. And so the number of linearly independent y's we could get here, which span the entire solution space, is of course the dimension of the solution space. So the topic of dimension now comes up as the number of functions you've got in a fundamental set of solutions, namely the ones that span everything else, which can also be seen as a basis of the solution space. And in the eigenvalue problems, they come up as the number of linearly independent eigenvectors you have to generate the entire eigenspace. And so just like here a general solution can be expressed as a linear combination of these fundamental solutions, in the same way any eigenvector could be expressed as for the same eigenvalue can be expressed as a linear combination of so let me actually write this as a linear combination of linearly independent eigenvectors. And so again, it's a concept of it's a kind of application of the concept of linear independence, where we're trying to see what is the number of linearly independent vectors we need in order to get a grasp of the entire structure, which in this case is eigenspace, and in the other case it's the space of solutions of linearly homogeneous linear differential equations. And so the number of vectors used there is called then the dimension of that space. And so that's how the two topics have this commonality. And again, the language which can express dimension in general is the language of a vector space. So you can see that there is a lot of similarities and commonalities between this topic of linear differential equations and the topic of studying matrices. And so they've kind of been put together by this general theory of vector spaces. Computationally, in terms of calculations you need to perform, most calculations are very specific to the context, right? The calculations you do here, for instance, that involves solving this characteristic equation and so on. And the funny thing is, here we also had something like a characteristic equation, right? This auxiliary equation that we were working out. So that's another analogy which we haven't actually made precise in the course, how the characteristic equation fits with the idea of auxiliary equation. I actually don't even know the answer to that question. The equation just came to me right now as I was explaining this. So it's beautiful when you see two completely different things kind of coming together nicely, and then unraveling the mathematical framework that explains this relationship, which is the framework of vector spaces, is a process that, of course, is absolutely fascinating. Now, but once we formalize this general notion of a vector space, then there are some computations that are brought in through this layer of work, which we might never have encountered in these two layers. And for example, one of them is the question we did just now when we were trying to prove that something was a vector space, right? This is the kind of computations we needed to do here. It's something we never encountered in these two specific areas. So by bringing in this new area, which allowed to extract some commonalities from the two specific places, also brought in its own specifics and its own techniques of computation. And one of the things there is this idea of a subspace, which is one vector space inside another one. And of course, it's another idea that's very relevant to the topics, because here eigenspaces are subspaces of the space Rn, and solutions form a subspace of the space of all functions. But once we identify the notion of a general vector space, then we might get other subspaces that are not of the form of an eigenspace or of the form of solutions of a homogeneous linear differential equation. Now, as I'm seeing that I'm not getting any specific questions, and since we are approaching to the end of the stream, what I want to do, for those of you who are fascinated by the mathematics we're doing here, I want to give you another example of a vector space, which is something very wild and different compared to the two examples we've been dealing with, these functions and the matrices. And I think that will kind of show you the power and richness of the notion in some sense. But in this example, I'm going to do something slightly different than what we've been doing up to this point. I'm going to change the nature of scalars. So imagine a world I think I've got a specific question now, which I will then address, and so we can leave this imagination for another time. Oh no, sorry, that was a request for next week's work. Okay, so imagine a world where we are working with scalars that are only allowed to be 0 or 1. Imagine scalars are just 0 and 1, no other scalars. So up to this point, we've been working with vector spaces where scalars can be any real number. Then we made some little remarks about the possibility of scalars being complex numbers. But now imagine that the scalars are just 0 and 1, nothing else. The first question there is that how we add things there. Well, if it's just 0 and 1, it's easy to multiply, right? 0 times 1 is 0, 1 times 1, so let's make a multiplication table, because scalars need to be added and multiplied, not just being called scalars, right? So here is the multiplication table for the world where scalars are just 0 and 1, and the addition table for 0 and 1 is the one where 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. Okay, so think about that. So 1 plus 1, we declare that to be 0. Okay, so that's the world of scalars. If that was the world of scalars, how would a vector space look like? So how would a zero-dimensional vector space look like? How would a one-dimensional vector space look like, and so on? So let's begin with zero-dimensional vector space. Zero-dimensional vector space has only zero vector. So it would just look like a dot. It's the same as how zero-dimensional vector space looks like when our scalars are all real numbers. What about one-dimensional vector space? So let's compare these pictures with the usual, the world of the usual scalars. So I'm going to make it almost like a table here, where on the right column, so this is our world of imagination, and this is the real life world, where scalars are all real numbers. Okay? A zero-dimensional vector space still looks like a dot, but a one-dimensional vector space, when scalars are real numbers, is a straight line. You've got the zero vector there, you've got a unit vector that spans that entire space. Since scalars are real numbers, we need to have one vector for each scalar. That's something that can be proved, by the way, that you need to have that. Now, when scalars are just 0 and 1, if we have a certain unit vector, okay, now all the other vectors we can get in this space spanned by this vector are scalar multiples of this vector, right? But if it's just 0 and 1, and I take this vector, I multiply it by 0, I get 0 vector, I multiply by 1, I get the same vector, and there's no other scalar to multiply this by. So this vector is going to span just this. So the one-dimensional vector space will be just two dots. Whereas here, when we had infinitely many scalars, we had an infinite straight line. And now, what about a two-dimensional vector space in this imaginary world? Well, in the case of the real world, where scalars are real numbers, a two-dimensional vector space is given by a plane, right? So why is it given by a plane? Well, because you've got, let's say you've got two vectors, right? Now you need all possible linear combinations of those to span a vector space, and then so you end up stretching them and then adding them by the parallelogram rule, and so you end up actually taking all possible vectors that lie on the entire plane, and it's an infinite plane. It doesn't really have a boundary, although I'm making a boundary here so that I indicate that I'm talking about the plane. Okay, what about in this case, if I have two vectors and I scale them and then add them, well, I can only scale them by 0 and 1, and if I scale each of them by 0 and 1, I get either the same vector back or the zero vector. And so it now remains just to add these two vectors to get the entire span. And when I add them, I get a third vector. So my two-dimensional vector space will be a square. And now you can start to see the pattern here, that the three-dimensional vector space in the real world, it was the usual real three-dimensional vector space, the space that kind of models our own three-dimensional space in which our physical bodies exist. Whereas in this world where scalars are just 0 and 1, if I begin with three vectors, let's see what I need to do to get all possible linear combinations. Well, scaling them doesn't change them. Either it leaves them or gives me zero vector, and zero vector plus anything is still that vector back. So scaling doesn't really affect anything. And what about just adding them? Well, we add these two, we're going to get that vector there, right? We add by adding those two. So that's the square we get out of those two. On the other hand, if we add these two, we get another square here. But now we could also add the bottom two, we get another square there. And we could also add all three together. And then well, okay, let's be careful here. So what's going to happen if I add these two, for instance? So let's give them names, v1, v2, and v3. What's going to happen if I take v1 plus v3 and I add, so which is that vector there, and I add that with, let's say, v2. So in other words, what's going to happen if I add all three of them? Well, if I take v1 plus v2, that's this vector, and by the parallelogram rule, we're going to get this thing here, right? So we end up getting a cube. Now, what about, yeah, I mean, that's all that we, I mean, in the other cases, we get something similar, and always it results in this edge here, in this vertex there. So a three-dimensional vector space in this world where scalars are just 0 and 1 is a cube. A two-dimensional one was a square. What about a four-dimensional one? A four-dimensional one will be a four-dimensional cube. What is a four-dimensional cube? How does it look like? There is a very nice illustration on Wikipedia, the one that moves. I'm just going to make a static one. So how do you draw a four-dimensional cube? Well, you first draw a three-dimensional cube. And how do you draw a three-dimensional cube? Well, the method is like this. You draw a line, then you duplicate the line, right? And then you connect the corresponding vertices. So that's how we get, out of one-dimensional space, we get two-dimensional space with scalars being just 0 and 1, right? Now, how did we get cube out of a square? Well, we take the square and we kind of shift it along that third vector that we are considering in our space. So we are shifting this along that third vector, right? So this is the third vector we want to have in a three-dimensional space, and we're shifting it along it so we get this cube. Okay, how do we get a four-dimensional thing? In a four-dimensional vector space, we would have a fourth vector that's linearly independent from these three. So let's draw it somewhere. Maybe we draw it, maybe I actually do the following. I move this thing over here and draw the fourth vector that must be linearly independent from these three that are given. I draw it somewhere there. Okay, and now all of the vectors I had here can be now added to that fourth vector, and by the parallelogram rule, that means I need to shift this whole picture. And so if I shift the picture, if I shift the picture, I need to shift it along this way, right? So I get something like that. Maybe I want to make it a bit shorter so that the picture is nicer. There we go. So I'm just making that vector a bit shorter. Okay, and then just like before, I connect the corresponding vertices. And what we get here is a picture of a four-dimensional cube, which now we know can be seen as, I hope I connected everything, can be seen as a model of a four-dimensional vector space in the case when scalars are just 0 and 1. Now, it is very difficult to imagine what a four-dimensional space where scalars are real numbers look like, but at least we have a very concrete picture of what a four-dimensional space looks like when the scalars are only 0 and 1. And there you go. So you see that there are some very fascinating vector spaces which have nothing to do with the vector spaces we are studying in this course, but where all the rules we established for those vector spaces we're studying now also carry over there. And one can do nice pictures with those and get some more inspiration for how beautiful mathematics is. Okay, great. So that brings us to the end of the stream. We now literally have like something like 40 or 30 seconds to complete the 2-hour session. And thank you everyone for joining. I will be streaming again next Friday at the same time, and we'll also be preparing some videos for the revision week, which will be posted to you by Monday morning as usual. Great. Have a nice evening and have a nice weekend, and see you another time. Goodbye.